Operation Paperclip is a story of contradictions that begins in the last days of the Second World War and winds its way through the Cold War, the space race, and the moral compromises made in the name of national security. When Nazi Germany collapsed in the spring of 1945, Allied forces fanned out across Europe to seize weapons, documents, and above all people. British and American intelligence officers were not just looking for blueprints or stockpiles of rockets. They were hunting the brains behind Hitler's war machine. The United States formed the Combined Intelligence Objectives Subcommittee, a joint effort with more than 3,000 technical experts, to locate scientists who could be useful to the Allies. In March 1945, a laboratory worker at Bonn University found a crumpled document in a toilet that changed the scope of the mission. Known as the Olsenberg List, it was a catalog of scientists and engineers considered essential to the German war effort. Those names would become targets for American agents racing against the advancing Red Army. The initial program to bring these specialists to America was called Project Overcast. Its official purpose was to interrogate about 100 prominent German scientists and employ them for 6 months to help fight Japan. Yet by August 1945, the war against Japan had ended. American planners saw a new threat rising in the Soviet Union and recognized that German expertise could tip the balance in the coming Cold War. The mission shifted from short-term interrogation to long-term exploitation. Paperclips were attached to the dossiers of candidates with troublesome backgrounds, giving the operation its later nickname. President Harry Truman approved the program in August 1946 on the condition that no known or alleged war criminals would be recruited. The Joint Intelligence Objectives Agency, created to run the project, quickly learned that the most valuable scientists had been party members or worse. To avoid losing them to the Soviets, officials simply removed incriminating evidence from their files. The promise of a fresh start in America outweighed moral qualms for both recruiters and recruits. Behind the scenes there was already fierce competition. The United States knew that the Soviet Union was running its own sweep, later called Operation Osaviekum, which would deport thousands of German specialists eastward in a single night. American officers wanted to secure not only the technologies, jet engines, chemical weapons, rocket designs, but also the people who understood them intimately. At the top of the Olsenberg list was Wernher von Braun, a charismatic engineer who had led the V-2 ballistic missile program at Peenemünde. Von Braun was a member of the Nazi Party and held a commission in the SS. He oversaw a program that used tens of thousands of concentration camp prisoners in underground factories. More than 20,000 people died in the Mittelwerk tunnels, according to a non-profit account. He personally recruited laborers from Buchenwald, and more than 3,000 of his missiles rained down on London and Antwerp, killing at least 9,000 civilians. Yet his engineering prowess was undeniable. When American forces reached Germany, von Braun and about 125 colleagues hid their V-2 documents in caves, stole a train and waited to surrender to the Americans. His younger brother Magnus approached U.S. troops waving a white flag and told them where to find the rocket team and their cache. They were promptly whisked away to the United States as War Department special employees. Von Braun's group arrived at Fort Bliss, Texas, and White Sands Proving Grounds, New Mexico, in 1946. The Germans helped the U.S. Army test captured V-2 rockets and develop prototypes of cruise missiles. In 1950, the team moved to Redstone Arsenal in Alabama to build ballistic missiles. Von Braun, meanwhile, cultivated an image as a visionary by writing magazine articles and appearing on television to explain space travel. After the Soviet Union launched Sputnik in 1957, his group, now numbering in the thousands and largely naturalized as U.S. citizens, helped launch America's first satellite, Explorer I. When NASA was formed in 1958, von Braun's division became the core of the Marshall Space Flight Center. He would design the Saturn V rocket that carried astronauts to the moon and later received the National Medal of Science. Such achievements make him an American hero in many eyes, yet they cannot erase his complicity in Nazi crimes and forced labor. The rocket team represented only a fraction of Operation Paperclip's intake. Roughly 1,600 German scientists, engineers and technicians, and their families, were relocated to the United States. Early recruits included experts in aerodynamics, guidance systems, jet and rocket propulsion, and aerospace medicine. The U.S. Air Force, Navy, and civilian agencies placed them in laboratories, universities, and private companies. Many were dispersed in small groups, which kept their presence out of the spotlight. In some disciplines, they accelerated American progress. In others, their impact was limited because American research programs were already underway. What unified them was the promise of residency and eventual citizenship in exchange for expertise. At the same time, their past political affiliations were minimized or hidden. The Cold War logic was simple. Better to have them working for us than for the Soviets. This moral compromise did not sit well with everyone. Eleanor Roosevelt and Albert Einstein were among prominent critics who warned against giving sanctuary to former Nazis. They believed that importing war criminals undermined the principles for which the Allies had fought. American officials responded by insisting that only good Nazis would be accepted, a claim that was disingenuous at best. While Truman's directive excluded known or alleged war criminals, agents circumvented it. Paperclips on dossiers signified that inconvenient details had been paper-clipped to the back rather than the front. Over time, public memory of the operation faded, replaced by images of rockets lifting toward the heavens. Beyond von Braun, there were other figures whose contributions and transgressions illuminate the program's complexities. Arthur Rudolph was an engineer who had managed production at Middlework, the subterranean factory where V-2 rockets were assembled by prisoners. Approximately 20,000 inmates died in those tunnels. After the war, Rudolph became a key figure in America's missile and space programs, serving as project manager for the Saturn V rocket. In the late 1970s, a survivor of Middlework wrote a book that renewed scrutiny of his wartime role. The U.S. Justice Department opened an investigation, and rather than face a trial, Rudolph renounced his American citizenship in 1984 and returned to Germany. His case shows how long it took for accountability to catch up with some paperclip recruits. Hubertus Strucode was another problematic figure. As the Luftwaffe's chief of aeromedical research, he oversaw experiments on concentration camp prisoners at Dachau. According to later investigations, prisoners were submerged in ice water, placed in low-pressure chambers, and subjected to brutal endurance tests. Yet after arriving in the United States, he pioneered space medicine. Strucode helped design pressurized suits and life support systems for the Gemini and Apollo missions. For decades, the American space medicine community lauded him, even naming an award after him. Only in the 1990s did revelations about his past lead organizations to strip his name from honors and reconsider his legacy. Strucode died quietly in 1986, having never faced trial. Kurt DeBus, a former V-2 test engineer and member of the SS, became the first director of NASA's Launch Operations Center, later the Kennedy Space Center, in Florida. He had been present at the Buchenwald concentration camp on at least one occasion and directed rocket launches at Peenemünde. Under his leadership, the Cape Canaveral facility evolved into the heart of America's crewed spaceflight program. DeBus frequently appeared in photographs with Presidents John F. Kennedy and Lyndon Johnson during the 1960s. Like von Braun and Rudolph, he built a second career by placing his expertise at America's disposal while his past receded into the background. The Air Force's recruitment of Hans von Ohain, the co-inventor of the turbojet engine, shows how paperclip reached beyond rockets. Von Ohain had developed jet propulsion technology for Germany. After the war, he worked at Wright-Patterson Air Force Base in Ohio. His British counterpart, Sir Frank Whittle, who had independently invented the jet engine, visited the Smithsonian Institution decades later and posed for a photograph with von Ohain. Their meeting symbolized the blending of once rival technologies under a new banner. Many paperclip scientists contributed quietly to fields such as guided missiles, supersonic aerodynamics, control systems, and aerospace medicine. Their work helped accelerate the development of ballistic missiles that would carry nuclear warheads. The program also fed into civilian industries. Companies like Bell Aircraft, General Electric, and Hughes Aircraft hired former German experts. This diffusion of expertise made it harder for the public to track who had been a Nazi and who had not. Some scientists obtained patents and built prosperous careers. Others struggled with English, culture shock, and the weight of their pasts. In this period, the Soviet Union, Britain, and France were running parallel programs to capture German knowledge. The Soviets relocated entire factories, including the Middlework V-2 plant and the Luftwaffe's Aviation Test Center, to Soviet territory. They conscripted German engineers as foreign experts and treated their work as war reparations. Western officials argued that because the Soviets were seizing talent by force, the United States needed to offer inducements to win the same talent voluntarily. The moral calculus of the early Cold War thus became a competition over who would benefit from the remnants of Hitler's regime. As Paperclip unfolded, internal reports occasionally acknowledged the uncomfortable truth that many recruits had been members of the Nazi Party or even the SS. Roughly half of the early Paperclip specialists had joined the Nazi Party, some opportunistically and others as true believers. A smaller number had joined paramilitary organizations like the SA and the SS. The rapid deterioration of relations with the Soviet Union after 1945 made American officials more willing to overlook such affiliations. They argued that the scientists' knowledge of rockets, jets, and nerve agents was too valuable to discard. Critics countered that this pragmatism came at the cost of justice for victims. The case of Georg Ricke illustrates both the rare exceptions and the prevailing impunity. Ricke had been director of middle work and was implicated in the use of slave labor and extrajudicial executions. He was brought to the United States under Paperclip, but later extradited to Germany for the Dachau trials. Ricke was indicted for collaborating with the SS and Gestapo, but he was ultimately acquitted. He returned to the United States and continued his career, suggesting how little accountability there was even when trials occurred. Decades later, the U.S. Justice Department would pursue a handful of elderly former Nazis under the Office of Special Investigations, but by then, most Paperclip scientists had retired or died. Public awareness of Operation Paperclip remained limited for decades because the program was classified and because its narrative conflicted with popular portrayals of World War II. When the New York Times and Newsweek reported on Paperclip in 1946, there was an immediate outcry. Government officials reassured the public that only apolitical scientists had been recruited. Yet the files released in the 1980s painted a different picture. Scholars and journalists revealed how the Joint Chiefs of Staff's 1945 memo had characterized the desired experts as rare minds whose continuing intellectual productivity we wish to use, and how many of those minds had been complicit in atrocities. The release of documents sparked debates about whether America's space program had been built on a foundation of moral compromise. Understanding Operation Paperclip requires grappling with its impact as well as its ethical cost. The program accelerated America's entry into the missile age and gave the United States an edge in the early Cold War. Von Braun's Saturn V rocket propelled astronauts toward the moon, and the research of former Nazi physicians contributed to aviation medicine. At the same time, the program shielded men who had participated in mass murder and human experimentation. Many victims never saw justice, and many perpetrators remade themselves into respectable American citizens. Paperclip shows how national security considerations can lead governments to make morally dubious bargains. When we watch footage of rockets soaring into space or celebrate milestones in science and technology, it is worth remembering the tangled roots of those achievements. Operation Paperclip was born from fear of Soviet dominance and the desire to harness knowledge that might otherwise be lost or used against the West. It brought to the United States people whose expertise helped shape the modern world. It also blurred the line between right and wrong, allowing war criminals to escape punishment as long as they were useful. The legacy of Paperclip is a cautionary tale about the choices nations make in moments of crisis and how those choices reverberate through history. In telling this story, we are compelled to confront the uncomfortable truth that the race to space was not only a triumph of human ingenuity, but also a product of human frailty and moral compromise. In the end, Operation Paperclip asks us to consider whether scientific progress can ever be separated from the ethics of those who advance it, and whether ends can truly justify the means. The last year of World War II left the European continent in ruins. Cities from Warsaw to Cologne were piles of rubble, and industries lay shattered. Yet amid this devastation, there were laboratories and factories where German scientists had achieved startling breakthroughs. The V-2 rocket represented the world's first long-range ballistic missile, while the first combat jets and sophisticated armor had already reached the battlefield. The Nazis had also stockpiled chemical munitions and begun to explore nuclear fission. As Allied troops crossed the Rhine and the Red Army closed in on Berlin, commanders understood that the war would end before they could capture all of this technology. Teams of experts roamed through laboratories in the Harz Mountains, Bavarian castles and underground bunkers, cataloging equipment, collecting documents, and interrogating personnel. It was a race not just for victory, but for technological inheritance. Washington's planners recognized that to harness such knowledge they needed an organized effort. The Combined Intelligence Objectives Subcommittee, CIOS, assembled more than 3,000 technical experts and reconnaissance teams. These specialists fanned out across liberated territories to identify research facilities and interview personnel. Their initial directive focused on special weapons, nuclear, biological, and chemical, and the means to deliver them. Reports produced by the CIOs confirmed that German scientists were far ahead of the Allies in several fields, including jet aircraft and advanced armor. In July 1945, the Joint Chiefs of Staff issued a classified memo titled Exploitation of German Specialists in Science and Technology in the United States, which described selected scientists as rare minds whose continuing intellectual productivity we wish to use. The memo never reached President Truman, but it guided the recruitment drive. The Olsenberg list, recovered from the toilet in Bonn, provided names and disciplines. Major Robert B. Staver of the U.S. Army used it to expand the scope of Operation Overcast beyond the original 100 interrogations. Werner von Braun himself was a study in contradictions. Born into an aristocratic family, he developed an early fascination with rocketry and joined a society of amateur rocket enthusiasts in his youth. He studied physics and engineering and quickly rose to become the technical director of the German Army's rocket program at Peenemünde. To secure resources, he joined the Nazi Party and accepted a commission in the SS. Under his direction, engineers turned the dream of spaceflight into the lethal reality of the V-2 missile, a 30-ton rocket that traveled faster than the speed of sound. The V-2's guidance system, propulsion, and aerodynamics were revolutionary, but its production was inseparable from brutality. After Allied bombing raids destroyed Peenemünde, production moved to the Mittelwerk tunnels near Nordhausen. Tens of thousands of prisoners from Buchenwald and other camps were forced to work underground in horrific conditions. Many died from starvation, disease, and executions. Von Braun later claimed that he was a technocrat who cared only about reaching the stars, but survivors remembered him touring the tunnels and ignoring their suffering. The satirist Tom Lehrer captured this moral blindness in a song. Once the rockets are up, who cares where they come down? That's not my department, says Werner von Braun. When the German rocket team arrived in Texas, they were initially isolated and under guard. Officially classified as prisoners of war and later as War Department special employees, they lived in barracks surrounded by barbed wire and needed passes to leave the base. They called themselves POPs, prisoners of peace, and knew that their status depended on their usefulness. Many began learning English and American customs. They gave lectures to Army personnel, played string quartets on Saturday nights, and built small rockets to demonstrate principles of propulsion. In the desert outside El Paso, they supervised the launch of captured V-2s as part of a program that gathered data on the upper atmosphere. At first, their wives and children were left behind in Germany. Eventually, families were allowed to immigrate and settled near Fort Bliss, forming a community that would later relocate en masse to Huntsville, Alabama. The scientists experienced culture shock, Texas heat, American food, differences in religion, but they also encountered opportunities unimaginable in post-war Germany. Their children enrolled in American schools and began to lose their accents, while their parents were granted increasing freedom as their value became apparent. The Redstone Arsenal assignment marked the next stage in the integration of the rocket team into the American military-industrial complex. At Redstone, they developed medium-range ballistic missiles and collaborated with American engineers on guidance systems and liquid fuel engines. The PGM-11 Redstone missile became the basis for America's first live nuclear ballistic weapon, while the Jupiter C and Juno launch vehicles derived from Redstone technology were used to launch early satellites. Von Braun's engineers worked on theoretical studies of staging and propulsion that would inform later designs. Their expertise accelerated the ballistic missile program, giving the United States credible deterrence as the nuclear arms race intensified. Although American rocketeers existed before Paperclip, the infusion of German experience provided tested design philosophies, especially in areas such as turbopump construction and engine cooling. At the same time, American universities began to train a new generation of aerospace engineers who would eventually eclipse their German mentors. Operation Paperclip was far more than the story of rockets. The 1,600 specialists who came to the United States encompassed chemists, physicists, physicians, metallurgists, engineers, and psychologists. Some developed supersonic wind tunnels and improved jet engines, enabling the X-plane program that would carry pilots beyond the sound barrier. Others worked on guidance and control systems, laying the foundation for modern avionics. Aeromedical researchers studied the effects of acceleration and weightlessness on the human body, information that would inform pilot training and later spaceflight. Not all contributions were beneficial. Several chemists had worked on nerve agents, and while American officials claimed such knowledge would be used defensively, the mere presence of these experts suggested an arms race in chemical warfare. The program's breadth meant that traces of Paperclip were woven into many Cold War technologies, from weather satellites to intercontinental missiles, even if the names of the Germans involved remained largely unknown. Arthur Rudolph's career exemplified the uneasy coexistence of achievement and atrocity. A mechanical engineer, Rudolph had been operations director at Middlework, overseeing slave labor and production quotas. Under Paperclip, he was placed at the Guided Missile Development Division in Huntsville and became project manager for the Pershing and later the Saturn V rockets. His leadership contributed directly to the successful Apollo missions. In the late 1970s, however, a survivor's memoir drew attention to his wartime role. The U.S. Justice Department's Office of Special Investigations accused him of participating in Nazi war crimes. Rather than face denaturalization proceedings, Rudolph surrendered his U.S. citizenship in 1984 and returned to West Germany. His case was unusual, not because he was guilty. Many Paperclip scientists had similar histories, but because someone attempted to hold him accountable. Kurt DeBus and Hubertus Struckold likewise avoided prosecution. DeBus served as director of NASA's launch operations, steering the Cape Canaveral facility through the Mercury, Gemini, and Apollo eras. Struckold, who had overseen hypothermia experiments on Dachau prisoners, became known as the father of space medicine after developing pressurized suits and life support systems for astronauts. Only in the 1990s did revelations about his past lead organizations to strip his name from honors. These examples show how accountability for Paperclip scientists was the exception rather than the rule. On the other side of the Iron Curtain, the Soviet Union implemented its own plan to capitalize on German science. In October 1946, the Red Army orchestrated Operation Osaviekim, a single-night operation that forcibly relocated more than 6,000 German specialists and their families to the Soviet Union. Soviet authorities dismantled factories, laboratories, and even entire research institutes, shipping them east. Engineers who had worked on rockets, aircraft, optics, and chemicals found themselves designing engines and missiles for Joseph Stalin's arsenal. Unlike Operation Paperclip, Osaviekim offered no employment contracts. The Germans were compelled to work under military supervision as a form of war reparations. Their contributions fed into the development of Soviet intercontinental ballistic missiles and the R-7 rocket that launched Sputnik. The existence of Osaviekim fueled American urgency and provided justification for recruiting former Nazis. If the Soviets were turning German knowledge against the West, American officials argued, then the United States was morally obligated to do the same, even if that meant making deals with men whose hands were stained with blood. When news of Operation Paperclip leaked to the press in late 1946, reactions were mixed. The New York Times and Newsweek exposed the recruitment of former Nazi scientists. Letters to editors decried the hypocrisy of sheltering men who had built Hitler's war machine. Eleanor Roosevelt wrote that the program violated the spirit of the Nuremberg trials, while Albert Einstein warned that employing war criminals would degrade America's moral standing. Military leaders countered that the scientists had been coerced into joining the Nazi Party and that America faced a new enemy. To reassure the public, officials emphasized that all recruits were vetted and that none had participated in atrocities, a statement that was demonstrably false. In fact, the Joint Intelligence Objectives Agency deliberately ignored evidence of Nazi affiliations. The files remained classified, and for decades the details of Paperclip were known only to a few historians and journalists. Popular culture celebrated von Braun and his colleagues as space pioneers without acknowledging their pasts. It was not until the 1980s that the U.S. government declassified many of the Paperclip files. Historians gained access to dossiers showing how recruiters had sanitized biographies and how officials had justified the inclusion of party members and SS officers. Books and documentaries revealed that roughly half of the early paperclip specialists had been members of the Nazi Party, and that some had joined the SS or SA. The revelations forced NASA and other institutions to confront their founding myths. Awards and buildings bearing the names of former Nazis were quietly renamed. School curricula and museum exhibits began to mention forced labor and the ethical cost of scientific progress. The conversation shifted from one of simple celebration to one of critical reflection about the price of Cold War victories. Many paperclip scientists embraced their new lives wholeheartedly. They bought houses, mowed lawns, and attended church picnics. Their children grew up in suburbia and enlisted in the U.S. military. Some divorced German spouses and remarried Americans. Others struggled with guilt or were ostracized by neighbors who learned of their past. Local newspapers in Texas and Alabama ran human interest stories about the German rocket boys, depicting them as quirky geniuses adjusting to barbecue and baseball. The community in Huntsville, nicknamed Rocket City, celebrated its heritage with festivals and museums. When the Apollo 11 crew walked on the moon in 1969, Huntsville held a parade for von Braun and his team. For many Americans, these immigrants were indistinguishable from other Europeans who had come seeking opportunity. Only decades later did a more nuanced picture emerge, one that acknowledged the privileges and protections they received compared with other refugees or immigrants. As the 1950s progressed, the knowledge gleaned from paperclip fueled a new arms race centered on intercontinental ballistic missiles. Engineers at Redstone Arsenal and private contractors across the country pursued designs capable of carrying nuclear warheads across oceans. The Soviet launch of Sputnik and later missions underscored the stakes of the competition. Von Braun argued that robust investment in rocket research could close the perceived missile gap, and his proposals influenced the deployment of the Atlas, Titan, and Minuteman missiles. Military planners spoke openly about mutual assured destruction, a doctrine that might never have emerged so quickly without the accelerated learning curve provided by former Nazis. The specter of missiles ready to fly at a moment's notice hung over the world for decades, a legacy in which paperclip played a hidden but significant role. The ethical controversy surrounding paperclip was intertwined with the post-war reckoning that produced the Nuremberg Code and the Universal Declaration of Human Rights. At Nuremberg, prosecutors documented the medical atrocities committed in concentration camps, including the hypothermia and low-pressure experiments overseen by Luftwaffe physicians. The resulting code established that human experimentation requires informed consent and that scientists bear responsibility for the consequences of their work. Yet even as the code was written, men like Hubertus Struckhold were being flown to the United States to continue research. Critics pointed to this contradiction. How could a nation champion human rights while benefiting from knowledge extracted through torture? Military leaders responded with a utilitarian argument that using such knowledge could save thousands of American lives in future conflicts. The tension between deontological ethics and consequentialist reasoning has persisted in debates about paperclip ever since. It has also influenced contemporary discussions about whether to use data derived from unethical experiments. In this way, paperclip is not just a historical episode, but a case study in the philosophy of science. Life in America was a complex mixture of gratitude and dissonance for many paperclip families. Housing provided by the Army was often basic, yet it was far superior to the bombed-out apartments they had left. Some scientists felt guilt leaving their war-torn homeland, while others saw their relocation as liberation from a totalitarian regime. They navigated a country grappling with its own issues of segregation and social change. In Huntsville, their children attended schools that were being desegregated under federal orders. They witnessed civil rights marches and listened to speeches by Martin Luther King Jr. The juxtaposition of American ideals and American realities offered its own lessons in hypocrisy. Several former Nazis became active members of local churches and civic organizations, seeking redemption or simply acceptance. Oral histories collected decades later reveal a range of emotions: relief at having survived the war, pride in technological achievements, shame about complicity in atrocities, and ambivalence about their adopted country. Museums such as the U.S. Space and Rocket Center celebrate the achievements of the engineers who put Americans on the moon. Exhibits often mention the German origins of rocket technology, but the ethical context is sometimes relegated to side panels. Scholars continue to argue about the extent of Paperclip's contribution to the space race. Some contend that American innovation would have prevailed regardless. Others assert that without German expertise, the United States would have fallen years behind the Soviet Union. Regardless of where one stands, there is consensus that Paperclip accelerated the exchange of ideas across borders, albeit under conditions shaped by war and ideology. As private companies now launch rockets and talk about colonizing Mars, the questions first raised by Paperclip about the sources of knowledge and the responsibilities of those who wield it remain relevant. Scientific progress does not occur in a vacuum. It is inseparable from history, politics, and ethics. Remembering Operation Paperclip requires holding multiple truths simultaneously. It is true that the program saved valuable knowledge from falling into Soviet hands and thereby strengthened the Western position in a dangerous era. It is also true that the program protected men who should have been held to account. Public memory tends to prefer simple narratives, heroes and villains, triumphs and tragedies separated by clear boundaries. Paperclip defies such neat categorization. Its participants were human beings capable of both brutality and brilliance. Its architects were patriots and pragmatists who believed they were acting in the national interest. Its critics were idealists who feared that moral compromise would poison the fruits of scientific progress. Historians must piece together declassified documents, survivor testimonies, and engineering reports to tell a story that acknowledges the light and the shadows. In doing so, we honor the victims of the Nazi regime and recognize the contributions of those who built the rockets that carried humans beyond Earth. We also learn a lesson about the dangers of letting expedience override principle. The program has become a cautionary tale in ethics courses and popular culture, illustrating how seemingly distant atrocities can shape present-day technology. As we grapple with emerging technologies, such as artificial intelligence, genetic engineering, and autonomous weapons, the questions raised by Paperclip resonate more strongly than ever. Are we willing to overlook potential harms in pursuit of competitive advantage? Who gets to decide when the ends justify the means? Remembering the full scope of Operation Paperclip encourages us to demand accountability, promote transparency, and ensure that innovation serves humanity. It challenges future generations to build a world where scientific achievement is inseparable from human rights for everyone. What if your thoughts were not entirely your own? In the anxious dawn of the Cold War, American officials seriously entertained that possibility. Pilots appeared in enemy newsreels confessing to crimes they had not committed. Prisoners of war recited careful scripts with unsettling composure. Newspapers amplified a new term, brainwashing, that made fear sound scientific. Within that climate, the Central Intelligence Agency authorized a portfolio of secret experiments meant to probe the mind's weak points and map the levers of influence. The program's sterile label hid its ambition, MK-Ultra. The premise was stark. If the mind is a system, perhaps the system can be disrupted, rewritten, and compiled again with different priorities. If loyalty is learned, perhaps it can be unlearned. If memory is pliable, perhaps suggestion can be folded into it. In 1953, CIA Director Allen Dulles placed the effort under the control of Sidney Gottlieb, a quiet chemist who ran the technical services staff. He specialized in the practical magic of espionage, gadgets, disguises, toxins, and MK-Ultra became his most audacious brief. It did not grow like a single tree. It spread like ivy, sending tendrils into universities, hospitals, prisons, and private institutes, each labeled as a subproject with just enough description to be plausible and not enough to be clear. Front organizations laundered funds. Intermediaries concealed who was asking the questions. Some professors understood they were working on problems of national security. Others received vague briefs about perception and behavior. Consent often blurred. Volunteers signed paperwork that hid crucial details. Patients were told that experimental procedures might help them, and prisoners were offered incentives they could hardly refuse. Even when signatures existed, the information was partial and the power imbalance overwhelming. LSD quickly became the signature instrument, not because it was tidy or predictable, but because it was powerful. In small doses, it could shift mood and time. In larger ones, it could pull a person far from the shoreline of ordinary consciousness. Could that instability be guided toward confession? Could a public breakdown be engineered to discredit an enemy agent? Could a suggestion settle more easily in a mind that had lost its anchors? These were operational questions. MKUltra did not confine itself to clinics. The agency established safe houses with one-way glass and hidden microphones, places where civilians were dosed without warning and observed like unwitting actors. Elsewhere, in psychiatric wards and prison wings, research blurred into exploitation. Records hid harm behind antiseptic terms, behavioral observation, non-therapeutic series, while the people described in those phrases stumbled through panic, memory gaps, and lingering distrust of their own perceptions. The program's ethic lagged far behind its ambition, and the nation would not learn that until much later. MKUltra did not appear from nothing. It evolved from earlier inquiries named BLUEBIRD and ARTICHOKE that explored hypnosis, sleep disruption, and drugs that might loosen tongues during interrogation. Under Gottlieb, the lens widened. The aim shifted from extracting information to reshaping minds. The agency funded work on psychochemicals, post-hypnotic suggestion, sensory manipulation, bright light exposure, sleep deprivation, and electroshock regimens that stretched well beyond ordinary therapeutic use. Grants flowed through innocuous-sounding foundations. Proposals used the language of behavioral science while avoiding the word control. LSD sat at the center, but many compounds orbited it: psilocybin and mescaline, scopolamine and barbiturates, stimulant-sedative combinations designed to confuse judgment and open a window for suggestion. Researchers mapped dose curves and peak windows, logged paranoia and euphoria, and noted how expectations shaped experience. The same amount might feel like a whisper to one subject and a thunderclap to another. Across notebooks, a principle emerged: minds are different, results are unstable. Leverage, if it exists, is probabilistic, not absolute. Field trials pushed the envelope. In agency safe houses, hidden microphones captured conversations after spiked drinks. Sex workers were paid to bring clients and then step out while the dose took hold. Technicians watched through glass, pencil scratching as if they were logging weather instead of people. Outside those rooms, unwitting dosing occurred at social gatherings and even at a retreat for government scientists, a choice that would echo in tragedy. Inside hospitals and prisons, volunteers lacked meaningful power to refuse. Environment proved as potent as chemistry. Sensory deprivation tanks and padded rooms stripped reality to monotone, erasing clocks until minutes blurred into hours and hours into fear. After sufficient isolation, a gentle script could feel like rescue, and a suggestion could sound like a lifeline. Bright light and constant noise dissolved time. Sleep deprivation sanded down skepticism. Hypnotists worked to implant post-hypnotic cues, words, tones, gestures meant to trigger moods, amnesia, or small actions days later. Electroconvulsive techniques were pushed toward depatterning, the hope that erasing enough structure would make room to write something new. Results were inconsistent. Some subjects became suggestible, others grew defiant. Some remembered nothing, others remembered too much. Failures accumulated in private while funding justified further attempts. Within headquarters, the moral arithmetic stayed the same. Measured risk to individuals was outweighed by potential strategic gain. In an adversarial world, officials argued, not to explore these methods was to fall behind an opponent who would explore them without restraint. The logic of necessity carried the day, and it would take years to dislodge it. Every covert system leaves fingerprints. MKUltras appeared as shell foundation checks, as memoranda stamped with code numbers, and as human lives bent around events they could not explain. The most famous fingerprint belonged to Frank Olson, an Army scientist who worked with biological materials. In November 1953, he attended a small retreat with CIA colleagues. Without warning, Gottlieb added LSD to the group's drinks. Olson unraveled in the days that followed: insomnia, distress, doubts about the ethics of his work. A week later, he fell from a hotel window in New York and died. The official account called it suicide. Years later, as fragments of MKUltra surfaced, the government apologized for the dosing and offered a settlement to Olson's family, though many questions remained. Was he simply the casualty of reckless experimentation, or did he know too much about methods that were never meant to see daylight? Competing theories persist, but the undeniable core is this: unconsented dosing helped push a human being past his breaking point. Olson's death became a symbol of a program that routinely treated people as instruments. His case was not the only crack in the wall. Rumors circulated about one-way, mirror safe houses, about wards where aggressive electroshock erased more than depression, about graduate studies whose funding sources never aligned. Some academics balked when they learned who their patrons were. Others looked away, preferring ambiguity to complicity. Inside the agency, compartmentalization kept the full picture out of view. The logic of secrecy was self-sealing. Because the work was sensitive, it required silence. Because it was silent, abuses flourished. By the mid-1960s, cultural winds had shifted. Civil rights, activism, anti-war protest, and growing skepticism toward authority made it harder to imagine indefinite impunity. Gottlieb retired in 1972. The following year, as scandal convulsed Washington, senior officials ordered boxes of MKUltra files destroyed. The purge succeeded in clouding the record. What remained were ledgers, scattered summaries, and the testimony of people on the receiving end. For investigators yet to come, the absence of documents would be as telling as their presence. Even so, the outline of the machine could be reconstructed from what was left behind. There had been unwitting dosing. There had been field trials in clandestine rooms. There had been experiments that turned hospitals and prisons into laboratories for national security. There had been a sincere conviction in many offices that such work was the price of safety. The question that would finally reach the public square was simple to ask and hard to answer. Who decided that price, and who consented to pay it? In 1975, the United States Senate convened the Church Committee to investigate intelligence abuses. What its hearings revealed stunned the public. Domestic surveillance that skirted the law, assassination plots contemplated in dry memos, and the outline of a mind-focused program that sounded like fiction until witnesses and documents made it fact. Reporters filed Freedom of Information Act requests. Families of victims sought counsel. Scholars began assembling timelines from redacted pages and reluctant testimony. Agency officials conceded key points. LSD had been administered without informed consent. Safe houses existed where civilians were observed after covert dosing. Universities and hospitals had received funds through fronts that obscured the sponsor. Reforms followed. Executive orders narrowed what intelligence services could do on domestic soil. Federal research rules codified protections for human subjects and placed informed consent at the center rather than the margins. The Belmont Report, institutional review boards, and improved oversight did not erase the past, but they reshaped the future. Court cases moved in tandem. Some plaintiffs prevailed, others hit walls built of classification and missing files. Meanwhile, historians and journalists mapped MKUltra's reach. They identified subprojects testing sensory deprivation and hypnosis, prison programs that paired barbiturates with stimulants in truth serum cocktails, and psychiatric regimens that blasted patients with electroshock far beyond therapeutic boundaries in the name of depatterning. The conclusion was twofold. There was no reliable switch for obedience. There was, however, a reliable set of pressures: isolation, fatigue, fear, and pharmacology used as force multipliers. Those pressures echoed through later decades. Training on interrogation learned to avoid visible marks while maximizing leverage. Psychological operations explored how expectation and framing could steer perception. None of this required magic. It required method and a willingness to treat people as systems to be tuned. That habit is subtle and durable. It appears wherever institutions prize outcomes over rights, plausible deniability over consent, and speed over scrutiny. The public reckoning mattered for another reason. It demonstrated that democratic oversight, while slow and imperfect, can still force secrets into daylight. Journalism, litigation, and legislative inquiry accomplished what internal checks failed to do. The cost of delay was paid by people who never agreed to participate. The benefit, if we choose to take it, is a set of guardrails that keep urgency from becoming licensed the next time fear arrives with a new name. What remains of MKUltra today is less a manual than a warning. It cautions that national security urgency can rationalize almost anything, that classified budgets, if not audited by outsiders, expand until they cover practices nobody would defend in public, and that science, without ethical ballast, can be recruited into projects that betray its purpose. Those are not antique concerns, they are perennial temptations. The 21st century reframes the same questions. If the last era asked whether chemicals and hypnosis could bend the will, this era asks how algorithms, attention markets, and intimate data shape habit and belief. Influence at scale is woven into everyday life. Recommendation systems steer what we notice. Interfaces reward what we repeat. None of this equals mind control, but all of it blurs the boundary between guidance and manipulation. Vigilance here is not paranoia. It is the ordinary work of drawing bright lines around consent, agency, and transparency. Healthy systems add friction where harm might occur. In research, that means independent review boards, meaningful and informed consent written in plain language, and protocols that welcome scrutiny instead of treating it as a threat. In intelligence, it means clear legal authorities, oversight with teeth, and inspectors general who can say no without ending their careers. These mechanisms are tedious by design. They slow the slide. Every missing memo in MKUltra's archive argues for more documentation, not less. Every redaction argues for clearer public accounting the next time secret work touches human lives. There is also a human ledger beneath the policy talk. Victims of non-consensual dosing and extreme regimens were not case numbers. They were people whose sense of reality, already fragile in some instances, was treated as material. Some rebuilt their lives with time and support. Others carried fractures that did not show on scans but shaped their days. Families were left to guess how a night in a safe house or a series of treatments altered the person they loved. Ethics lives here, in the grain of experience, not merely in elegant rules. The good news is that lessons can be reclaimed. Psychopharmacology now proceeds under standards that center the patient. Neuroscience maps perception with humility about complexity. Clinical ethics is a profession, not an afterthought. Curiosity, when coupled with conscience, can illuminate rather than exploit. That coupling, ambition with accountability, is the real antithesis of MKUltra. The story of MKUltra does not end with a device that commandeers thought. It ends with a set of choices societies must make again and again. Secrecy magnifies error. Fear is a poor architect. Urgency tempts us to trade process for promise and to rename caution as weakness. The antidote is steadiness, methods that can survive inspection, records that can be audited, and a civic culture that rewards accountability instead of confusing it with disloyalty. Look closely at how the truth surfaced. It did not arrive as a voluntary confession. It arrived through journalism, lawsuits, congressional inquiry, and the stubborn patience of families who refused to let the record vanish. File destruction slowed the reckoning but could not erase it. Enough fragments remained to teach what needed teaching. Each time a researcher over-explains a study to ensure understanding, each time an oversight board demands revisions before approval, each time a legislator insists on narrower authorities with clearer reporting, the world that made MKUltra possible recedes a little further. The mind is not a code base that can be patched at will. It is a living weave of biology, memory, emotion, culture, and story. You can frighten it and numb it, you can disrupt it and tilt it. You can push choices toward a preferred outcome by narrowing options and saturating cues. But plasticity cuts both ways. The same flexibility that permits influence also permits recovery. People find language for what happened. Communities grow norms that protect the vulnerable. Law draws lines. History supplies examples that remind us why those lines exist. It is tempting to cast heroes and villains in hard edges. The reality is more useful and more unsettling, a spectrum of responsibility. Some designed experiments they knew violated ethics. Some kept distance from the mess and told themselves they were only studying phenomena. Some raised concerns and were ignored. Some refused to participate. The lesson for the present is practical. When a bright initiative arrives wrapped in urgency and vagueness, ask questions before momentum makes answers irrelevant. Who can opt out? Who can review from the outside? What happens to the data? What harm is plausible? And who will carry it if things go wrong? MKUltra tried to master the mind and failed, but its residue lingers, in rules that demand informed consent, in committees that ask aggravating questions, in the skepticism we bring to claims of necessity that arrive without details. The most durable protection for human thought is not a gadget or a doctrine. It is a habit of refusing to treat people as means when ends look bright and urgent. Each time we practice that habit, we honor those used in secret and choose a future where science and freedom stand on the same side.
The first interstellar object, 1I/Oumuamua, defied expectations. Detected in October 2017 by the Pan-STARRS Survey Telescope in Hawaii, it was unlike any comet or asteroid seen before. It was relatively small, about 400 meters long, but its shape was extraordinary, perhaps 10 times as long as it was wide, like a cosmic cigar or needle. As it tumbled through space, astronomers noticed its brightness would swing wildly, implying a dramatic elongation and irregular shape. There was no visible coma, no tail, no obvious jets of gas venting from its surface. Oumuamua appeared inert and rocky, prompting debate. Was it a fragment of a shattered planet? A dried-out comet that lost its ices? Its surface was slightly reddish, hinting at long exposure to cosmic rays in interstellar space. It traveled a path suggesting it came from the direction of Vega and Lyra before drifting for hundreds of millions of years through the galaxy. Upon slingshotting around the sun, it sped back out, headed toward Pegasus, never to return. One more puzzle came from Oumuamua's behavior. As it exited our solar system, it sped up slightly, a tiny but detectable non-gravitational acceleration. Typically, comets do this by venting gas and dust like a rocket, but telescopes saw no such outgassing clearly. This mystery led to a whirlwind of theories. While most scientists concluded a hidden comet-like activity, perhaps releasing invisible hydrogen or extremely fine dust, was nudging it, a few voices speculated more exotic possibilities. Could it be artificial, a derelict spacecraft, or a probe sent by an alien civilization? The notion captured headlines, though nearly all experts assert that Oumuamua was natural. Still, the mere suggestion of an alien artifact sparked the public's imagination, cementing Oumuamua's legacy as one of the most enigmatic objects ever found. In contrast, 2I/Borisov seemed more familiar. Discovered in August 2019 by Gennady Borisov with a homemade telescope, this visitor looked and behaved like a typical comet in many ways. Borisov had a visible coma, a fuzzy halo of gas and dust, and a tail that extended millions of kilometers as it neared the sun. Telescopes quickly confirmed its path was hyperbolic, an open-ended trajectory that proved it came from interstellar space. Astronomers around the globe scrambled to observe it. The Hubble Space Telescope captured images of Borisov in late 2019, showing a bright core of dust and a stable coma. Unlike Oumuamua, which was elusive and detected only after it had passed the sun, Borisov was discovered inbound, giving scientists ample time to watch it evolve. They saw it brighten and then fade just like a normal comet. In early 2020, Hubble even noted that a fragment might have broken off its nucleus, again something not unheard of for active comets. Yet Borisov had its own surprises. Spectroscopic studies revealed that its chemical makeup was unusual. It was very rich in carbon monoxide, far more than any solar system comet at a similar distance from the sun. Carbon monoxide is a very volatile gas that requires extremely cold conditions to freeze into ice. The excess CO hinted that Borisov formed in a frigid environment, perhaps in the outer reaches of its home system, maybe around a cool red dwarf star or in a cold primordial disk of a young star. This was a tantalizing clue to its origin. If its cometary ices condensed in an extremely cold region, Borisov could be a fragment from the far outskirts of an alien solar system, a chemical ambassador from a place where ices we rarely see can survive. Researchers even speculated it might be a piece of a small, icy world or a fragment of a dwarf planet's crust, rich in CO ice. By the time Borisov swooped past the sun, reaching perihelion in December 2019, and headed back to the stars, it had provided a wealth of data. Its nucleus was estimated to be only about 0.9 to 1 kilometer across. It raced through the inner solar system at about 110,000 miles per hour, 177,000 kilometers per hour. And critically, Borisov demonstrated beyond any doubt that comets do visit us from other stars. Whereas Oumuamua appeared to be a rock, Borisov is really active, more like a normal comet. It's a puzzle why these two are so different, remarked one astronomer. The stark differences between the first two interstellar objects, one dry and asteroidal, the other icy and cometary, taught us that interstellar visitors come in assorted guises, reflecting the diversity of their origins. These early lessons set the stage. With two interstellar objects spotted back-to-back, scientists anticipated that more lay hidden in the cosmic deep. Surveys were expanding, new telescopes were coming online, and our eyes were open to the possibility of additional visitors. Indeed, astronomers suspected that in the vast reservoirs of comets in our own solar system, like the distant Oort cloud, some are occasionally flung outward to become wanderers in interstellar space. The wait for the next interstellar visitor was not long. In late June 2025, the ATLAS survey, a network of automated telescopes designed to hunt for asteroids on collision courses with Earth, picked up a faint moving point of light in the constellation Sagittarius. On July 1, 2025, the ATLAS telescope in Rio Hurtado, Chile, reported the object to the Minor Planet Center. At first glance, it seemed like just another new comet discovery. It was given a provisional designation C/2025 N1 ATLAS. But very quickly, as observatories around the world started tracking it, the truth became clear. This object was traveling far too fast and on too strange a path to be a local comet. Follow-up observations poured in, including pre-discovery images taken weeks earlier in mid-June. All data confirmed an open-ended trajectory. The object wasn't bound to the sun at all, it was merely paying us a visit. By July 2, 2025, the Minor Planet Center announced it as an interstellar object, formally designating it 3I/ATLAS, the third of its kind. There was excitement but also caution born of experience. We now knew interstellar objects come in different forms. What was 3I/ATLAS going to be like? Early reports suggested it possessed a fuzzy coma, hinting at a cometary nature. As more images came in, it was evident that 3I/ATLAS was surrounded by a cloud of dust, albeit a small one. It was not a stark point of light. It had the hazy look of a comet. The Atlas in its name recognized the discovery team, while the I stands for interstellar, and the 3 marks it as the third such object. Anticipation built swiftly. This time, unlike Oumuamua, we had found the visitor early, with months ahead of it moving through our solar system. The astronomical community mobilized rapidly, determined to study this alien wanderer in unprecedented detail. News of the discovery spread quickly beyond scientific circles. The world learned that yet another interstellar interloper had entered our cosmic backyard. Across continents, telescopes large and small tracked 3I/ATLAS against the stars, gathering photons that had bounced off a traveler born in a distant sun's embrace. Humanity was ready to learn whatever secrets this visitor carried. If we could trace the path of 3I/ATLAS through space, it would look like a vast open curve, a hyperbola, piercing the solar system. Unlike the closed loops of planets and ordinary comets, a hyperbolic trajectory is one of escape. This object came from afar, is cruising through our sun's domain, and will head back out to interstellar space, never to return. In practical terms, the sun's gravity is not enough to capture 3I/ATLAS. It's moving too fast and on too unbound a path. How fast? When 3I/ATLAS was first observed in June 2025, it was about 670 million kilometers from the Sun, near Jupiter's orbit, and already cruising inward. It approached from the general direction of the constellation Sagittarius toward the dense star fields near the Milky Way's core. As it fell toward the Sun, like any comet, it accelerated, trading gravitational potential for speed. By the time it reached the inner solar system, 3I/ATLAS was moving incredibly fast, over 130,000 miles per hour, 210,000 kilometers per hour, relative to the Sun, and climbing. For comparison, that's about 58 kilometers per second, faster than any spacecraft humans have ever launched, and a record among the 3 interstellar objects observed so far. Importantly, 3I/ATLAS's trajectory was not steeply inclined or perpendicular to the planetary plane. It was arriving on a path only slightly tilted relative to the ecliptic. In fact, its orbit is retrograde, moving in the opposite direction of the planet's orbits, but nearly flat along our solar system's plane. Some might call this a coincidence. Others note the plane of our solar system isn't far off from the plane of the galaxy's disk, so an interstellar object from the galactic disk might naturally come in on a similar incline. Nonetheless, such an alignment is statistically uncommon. For practical planning, what mattered to astronomers charting its course was that 3I/ATLAS would make a relatively gentle passage through the inner solar system. It was not going to come particularly close to Earth, at nearest about 1.8 astronomical units away, roughly 270 million kilometers, or 167 million miles, about as far as Mars is from us. In early October 2025, it would pass about 70 million kilometers from Mars, giving the fleet of spacecraft there a chance to observe it from a different vantage. Then it would slip behind the Sun from Earth's perspective in late October, surviving a perihelion at about 1.4 astronomical units, just inside the orbit of Mars, around October 29th. After that, it would swing back outward, crossing Venus's orbital distance, with Venus nowhere near that point, in early November. By March 2026, forecasts showed it passing Jupiter's orbit, on the far side from Jupiter itself, and continuing its escape. The Sun's gravity would bend its path but ultimately not hold it. 3I/ATLAS came in on a one-way ticket. The orbital eccentricity calculated for 3I/ATLAS was about 6.1, an extremely high value. For reference, a perfect parabola is approximately 1 and a circle is 0. This confirmed its status as a hyperbolic comet with a lot of excess velocity. In plainer terms, even after escaping the Sun's pull, it will still be moving at tens of thousands of miles per hour relative to the stars. Such speed can only be gained by being tossed out of another star's gravitational well long ago. This dynamical evidence, speed and trajectory, was airtight proof that 3I/ATLAS is not from here. No comet that originated in our solar system, even from the far Oort cloud, would naturally have such a hyperbolic orbit unless something truly extraordinary happened. Once 3I/ATLAS was identified as an interstellar interloper, an unprecedented observational campaign sprang to life. Space-based assets turned their eyes toward the visitor. The Hubble Space Telescope observed the comet as early as July 2025. The James Webb Space Telescope, JWST, with its infrared eyes, followed in early August. A UV-sensitive space observatory captured the subtle glimmer of hydroxyl in the comet's vicinity. Even spacecraft further afield joined the effort. The Mars rovers and orbiters prepared to snap images during its Mars-adjacent passage, and a Jupiter-bound probe planned an attempt to collect data as 3I/ATLAS passed by in 2026. It seemed every available eye in the solar system was turning to watch this small cosmic visitor. Never before had an interstellar object been observed with such a coordinated, high-powered fleet of instruments. Hubble's early images, taken when 3I/ATLAS was about 277 million miles from Earth on July 21, 2025, revealed a teardrop-shaped cocoon of dust surrounding a bright nucleus. Because Hubble was locked onto the speeding comet, background stars appeared as short streaks, a vivid reminder that this object was in motion, an interloper against the fixed stellar backdrop. From these observations, scientists began estimating the size of the comet's solid core. By late August 2025, data suggested the nucleus of 3I/ATLAS was at most about 5.6 kilometers, 3.5 miles, in diameter, and possibly as small as around 440 meters, a quarter mile, across. That upper estimate, a few kilometers wide, would make 3I/ATLAS several times larger than Borisov and vastly larger than diminutive Oumuamua. If 3I/ATLAS truly is approximately 3 to 5 kilometers in size, it would be by far the largest interstellar object ever detected. Some later estimates put it between 5 and 11 kilometers, though these numbers remain preliminary as observations continued. In any case, 3I/ATLAS appeared to be a significant hunk of material carrying perhaps billions of tons of mass from another star system. On the ground, large observatories got to work as well. The Gemini South Telescope in Chile captured a remarkable photograph of 3I/ATLAS in July 2025, showing a classic cometary appearance, a bright diffuse head and a faint tail trailing behind. At first glance, one might not distinguish it from a normal comet of our own solar system. It had a slight greenish tint in some images, a common feature of comets rich in certain gases, and as weeks went by, observers noted its tail grew in length. It even displayed an unusual phenomenon, what looked like a backward tail. Normally, a comet's dust tail is pushed away from the sun by radiation pressure, so it trails behind the comet relative to its path. But 3I/ATLAS showed a stream of larger dust grains being pushed in the direction of the sun by the comet's own outgassing pressure, essentially heavy particles expelled by jets that sunlight couldn't immediately blow away. This created the appearance of a secondary tail pointing sunward, a striking and rare sight sometimes called an antitail. It was a vivid display of how active 3I/ATLAS was, venting material vigorously as it warmed. Early on, 3I/ATLAS was indeed noted to be unusually active for how far it still was from what truly excites scientists about capturing an interstellar comet are the clues it carries in its chemistry. Here is an object formed around another star, preserving perhaps the very building blocks of its original planetary system. By splitting the comet's light into spectra and analyzing the gases it releases, we can read a chemical letter from a distant place. As one astronomer put it, when we detect water, or even its faint ultraviolet echo, OH, from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. In July 2025, ultraviolet observations detected a surge of hydroxyl OH molecules coming from 3I/ATLAS. O forms when water, H2O, is broken apart by sunlight's UV rays. Detecting OH around a comet is a proxy for detecting water, and it was seen when the comet was a remarkable 2.9 astronomical units from the Sun, nearly 3 times farther out than Earth's orbit. At such a distance, sunlight is weak, and typically water ice is still too cold to sublimate in large amounts for ordinary comets. Yet 3I/ATLAS was already gushing water vapor. Researchers calculated it was shedding roughly 40 kilograms of water per second at that stage, about the flow of a fire hose on full blast. The image of a fire hose of water blasting from an interstellar comet before it was anywhere near the sun captured imaginations and challenged models. This early water activity suggested intriguing possibilities. Either 3I/ATLAS had very volatile ice just below its surface, so that even a little solar warmth at 3 astronomical units released it, or it had an abundance of very small ice grains that heat up quickly. A study at the end of September 2025 provided clear evidence of distant water outgassing and proposed that tiny icy grains on the comet's nucleus were being warmed by sunlight and vaporizing to produce the observed OH signal. This hinted that comets from another star might have different textures or grain properties that affect how and when they release water. Meanwhile, the James Webb Space Telescope targeted 3I/ATLAS with its superb infrared spectrographs. Initial observations indicated that 3I/ATLAS has a high carbon dioxide to water ratio in its composition. CO2 ice sublimates at higher temperatures than water ice. The fact that CO2 seemed plentiful compared to H2O suggested that 3I/ATLAS might have formed far from its parent star, where CO2 ice could freeze alongside water ice. In our solar system, for instance, CO2 ice forms in the cold realms beyond Saturn. These data pointed to a comet rich in carbon dioxide and dovetailed with the early water activity. If it is losing water at 3 astronomical units, its ices likely include more volatile components like CO2 or CO that can jumpstart activity far out. Another curious detection involved nickel in the comet's coma, apparently without much iron. On Earth, nickel and iron are often found together. Some reports indicated nickel was observed outgassing with no corresponding iron line. One theory was that this could reflect origin in a metal-poor environment, as might occur around older stars. Others cautioned it might simply be that nickel-bearing molecules like nickel carbonyl sublime more readily than iron compounds. It's a technical point, but one seized by those inclined to speculate about artificial origins. However, mainstream researchers saw it as another piece of the compositional puzzle, likely explainable by natural processes given the right conditions. As the comet drew closer to the Sun through late 2025, astronomers monitored its evolution. Many expected it to brighten and perhaps develop a more prominent tail or a green glow as solar heating ramped up. The green color in comets comes from molecules like diatomic carbon or CN being broken apart by sunlight. Indeed, by October, some images showed a faint emerald hue, suggesting complex chemistry at work. In essence, 3I/ATLAS behaved like a dynamically young comet, one that perhaps had never been near a star since its formation. Every observation was a precious data point: the color of its dust, the ratios of gases, the shape of its coma, the flux of material. One of the most profound questions about an interstellar visitor is, where did it come from? With Oumuamua and Borisov, astronomers attempted to backtrack their incoming trajectories to identify candidate origin stars, but with little luck. The uncertainties were too large and the objects had been wandering too long, perturbed by unknown encounters. With 3I/ATLAS, an international team endeavored to do the same, using precise stellar positions and motions. By rewinding the clock on 3I/ATLAS's trajectory and checking it against the past motions of nearby stars, they hoped to pinpoint if it had passed near any star in the last few million years. The results were intriguing. Tracing 3I/ATLAS's path back some 4.3 million years, the study identified dozens of star systems that the comet had come moderately close to in that time. But none of those encounters could account for the comet's current speed and direction. None seemed to be the home that kicked it out. The gravitational tugs were negligible. This implies that 3I/ATLAS did not originate anywhere near our Sun or its immediate stellar neighbors. To explain its high speed and hyperbolic orbit, one must go back much further and likely to a far more distant origin. The researchers hypothesized that 3I/ATLAS is extremely old, perhaps having traveled on the order of billions of years through the Milky Way. One scenario that fits the data is that it was born in the formative days of our galaxy, in a region perhaps at the border between the Milky Way's thin disk and thick disk. The thin disk hosts most familiar stars, including the Sun, and is relatively young and metal-rich, while the thick disk is older and more metal-poor. The wild frontier between these two populations could be a place where dynamic interactions were common and where primordial objects could be ejected. According to one analysis, 3I/ATLAS may be on the order of 10 billion years old, more than twice as old as our solar system. If true, that is astonishing. A time capsule from the early Milky Way formed around a star that was among the first in the galaxy to have planets, or even from a protostellar cluster that no longer exists. It might have been wandering the galaxy since before Earth even existed. Over such vast time, it would have crossed spiral arms, passed near supernovae through interstellar clouds and experienced the subtle gravitational pulls of countless stars, a true galactic odyssey. How did it get ejected in the first place? The prevailing theory is that such objects start in the outskirts of a planetary system, akin to our Oort cloud, and are flung into space by gravitational interactions. In our solar system, many Oort cloud comets were likely thrown outward by close encounters with giant planets long ago. In the same way, 3I/ATLAS might have had a brush with a giant planet in its original star system, or a passing star perturbed its orbit, giving it escape velocity. Once adrift in the galaxy, it essentially became an ice rock castaway, destined to roam indefinitely unless captured or destroyed. Pinpointing a specific parent star for 3I/ATLAS remains highly uncertain and probably impossible with current data. Beyond a few million years, the cumulative effect of random tugs and the sheer scale of time erases the trail. So, while we likely won't ever know which star it came from, the evidence suggests a general origin, perhaps an ancient metal-poor environment in the outer reaches of the galaxy. This aligns with the chemistry hints. The high CO2 content and nickel/iron oddities might be fingerprints of a system with different elemental ratios. With 3 interstellar objects now in hand, we have the beginnings of a sample set, small but incredibly instructive. Oumuamua, a 100 to 150 meter shard, elongated, no coma, a slight non-gravitational acceleration, reddish surface, discovered post-perihelion and gone before we could study it in depth. Borisov, a textbook comet approximately 1 kilometer across, active with a visible coma and tail but unusually rich in CO, suggesting a frigid birthplace. Atlas, volatile rich, unusually active far from the Sun, possibly several kilometers wide, displaying anti-tail dust dynamics with a high CO2/H2O ratio and early OH detections at 2.9 AU. Side by side, they show a startling diversity, no two alike, implying that ejected planetesimals from other stars span a wide range of compositions and histories. One common thread unites them. Each became an exile through gravitational dances, giant planets and stellar flybys swapping material across the galaxy and connecting planetary systems through drifting messengers of ice and rock. The arrival of 3I/ATLAS ignited a flurry of activity not just in telescopes, but in the scientific community at large. Dozens of astronomers and planetary scientists specializing in comets, astrobiology, and planet formation turned their attention to this interstellar interloper. Within weeks of its discovery, analyses of its orbit, potential origin, and early spectra circulated widely. Public-facing tracking tools were updated so enthusiasts could follow its path in real time. There was a palpable sense of excitement. With an interstellar comet passing through our own solar system, it's as if a sample of a planet-forming disk from another star has shown up in our backyard. Researchers were keen to squeeze every bit of information out of it before it departed. International collaboration defined the campaign. Teams coordinated observation schedules across continents and wavelengths. Radio dishes probed gas signatures. Optical telescopes tracked brightness and structure. Ultraviolet and infrared instruments dissected the composition. The Minor Planet Center served as the clearinghouse for positional data, enabling precise trajectory updates that let even amateurs know where to point their telescopes. Public interest grew with each new discovery: water seen at great distance, CO2-rich makeup, a possible green glow, and headlines amplified the unfolding story. As with Oumuamua, speculation about alien technology inevitably surfaced. A provocative paper mused that 3I/ATLAS's low inclination, nearly coplanar path could favor a hypothetical probe using the Sun for a clandestine maneuver. The idea made waves but collided with the weight of evidence. Everything observed about 3I/ATLAS looked like a comet and behaved like a comet. Detailed rebuttals noted that a low inclination can naturally arise for interstellar bodies originating in the galactic disk. that the hyperbolic speed and eccentricity match gravitational ejection expectations, that the odds of close planetary encounters were low and unremarkable, that the colors and spectra matched known comet classes, and that no anomalous accelerations suggesting propulsion were detected. Extraordinary claims require extraordinary evidence. For 3I/ATLAS, the evidence points firmly to a natural origin. Culturally, interstellar objects rekindle a sense of wonder about our place in the cosmos. People ask, could such comets ferry life's ingredients between stars? While 3I/ATLAS is far too cold and airless to harbor life, the detection of water and organic bearing molecules underscores that the building blocks of biology are widespread. In a real sense, these visitors bridge hard data with philosophical reflection. They remind us that the universe trades materials across light years, and occasionally one such messenger drifts past for us to study. As 3I/ATLAS continued on its way, past Mars's orbit in early October 2025, around the Sun in late October, outward again toward the dark, its legacy came into focus. It left a trove of scientific data, evidence that even an ancient comet carries water and carbon across the stars, motivation to broaden theories of comet activity to include vigorous outgassing far from the Sun, hints that a comet's chemistry can encode the structure and history of the Milky Way itself. It also showcased humanity at its collaborative best, telescopes on Earth and in space working in concert, professionals and amateurs sharing the sky, all focused on something not of this Earth and not of this Sun. Looking forward, many expect a golden age of interstellar object studies. New wide-field surveys will likely find more, perhaps many more. Missions like ESA's Comet Interceptor, designed to wait in space and sprint to a newly found comet, may one day rendezvous with an interstellar target. Imagine holding a sample from another star system, alien ice and dust formed in a faraway dawn. Until then, we rely on telescopes and clever analyses, and even with those alone, look how much we've gleaned. Cold, CO-rich nurseries around other stars inferred from a single passing object, textures of cometary ice hinted by OH at 3AU, a time capsule perhaps older than the solar system itself drifting briefly into our ken. There's a humbling aspect to it all. These objects are small and faint. Without diligent surveys and a dash of luck, we would never notice them. Oumuamua slipped by after the fact. Borisov was spotted by a patient amateur. Atlas was found by a system designed to protect Earth that happened to net a traveler from another sun. It suggests our catalog is just the tip of the iceberg. Perhaps they inspire kinship with distant worlds. In a universe that can feel isolating in its vastness, these drifters are reminders that we are connected to the galaxy by threads of wandering ice and dust. The camera of imagination follows 3I/ATLAS as it leaves our solar system, the sun dwindling behind, the infinite night ahead. Will it wander for another billion years? Will it pass some other inhabited world and spark curiosity there as it did here? In the silence of space it carries on, a voyager from an unknown dawn, a messenger of the stars, and a reminder that the cosmos is richer and more wondrous than we ever believed.